This video is for Module 2, Part 5, and includes a discussion of the binomial probability model and how to obtain those probabilities using a spreadsheet. Okay, let's go ahead and get started. So up to this point, we've been using the reference distribution app to obtain our p-values. We can also use a spreadsheet to obtain these p-values. And the spreadsheet actually uses a binomial probability model for its calculations. So let us first reconsider the analysis of the males from the WSU Vitamin A case study. The research question there was, is there enough statistical evidence to say that WSU males are off target from their daily recommended intake of vitamin A? This was a two-tailed analysis, and the observed outcome was 3. So we had 3 males that were over their daily recommended intake for vitamin A. Now, as I've said, up to this point we've been using the reference distributions that have been obtained from simulation models. 2 different simulation models will produce slightly different reference distributions. The p-values obtained using these reference distributions, which implies that 2 different simulations will produce slightly different p-values. So let's just show 2 simulations here. Simulation number 1 was based on 5,000 repeated outcomes. My p-value that we obtained from this reference distribution here is 0.0518. A second simulation was obtained, and the p-value that we obtained from the second simulation was 0.0572. Notice that both of these p-values are pretty close to that 0.05 threshold. But in each case, they do not meet that 0.05 threshold, so we do not have enough evidence to say that WSU males are off of their target for vitamin A. However, we do recognize that those p-values are close to that 0.05 threshold, as I've stated. Now, a researcher could ignore one simulation model in favor of another in order to get a p-value less than that 0.05 threshold. Now, once that p-value is below the 0.05 threshold, we get to say that the data provides enough evidence for our research question. So there's a strong incentive to get that p-value less than 0.05. However, we don't want a researcher tossing out one simulation model in favor of another just so they can obtain a significant result. The binomial probability model solves this problem. The binomial probability model the binomial probability model will alleviate that problem that I just mentioned. So how does it do that? Well, the binomial probability model is based on an infinite number of repeated samples. So if we come back up here and look at our simulation distributions that we obtained up here, we used 5,000 repeated outcomes. The binomial probability model uses an infinite number of outcomes. So in that sense, it's a mathematical result. That results, or what that means, is that 2 different statisticians will get exactly the same p-value. So for that reason, the binomial probability model is attractive in that a researcher would not be able to obtain, say, a different simulated model to get a different p-value. We'll always get the same p-value when using a binomial probability model. So the binomial probability distribution has the following form here. The formula is actually kind of ugly. We're going to let the spreadsheet do all of the calculations for us. Some of the syntax here, this probability of outcome is equal to x, is just the probability of x occurring. The factorial notation, so n factorial, or let's suppose that n was 4. What 4 factorial stands for is we would just take 4 multiplied by 3, multiplied by 2, multiplied by 1. So we just go from that value all the way down and multiply those together. Pi here is just my parameter of interest. N is the number of trials, and x is the probability that I'm interested in calculating. There are conditions for a binomial probability model. In fact, any statistical model that we would use would have conditions associated with that. 3 of these conditions we have brought up several times. So what are 3 of the first one is there's 2 possible outcomes. The second, there's a fixed number of trials. The third is the probability of success is the same from one trial to the next. And then a fourth one, which has not been mentioned up to this point, is that the trials need to be independent of one another. So what that means is one outcome cannot be influenced by another. So let's just real quickly discuss whether or not the assumptions are being met for the WSU Vitamin A male case study. So did we have 2 outcomes? We did. The outcome of interest was that they were either over or under their daily recommended intake. So one of 2 possible outcomes there. Fixed number of trials. We did. We had 14 males in our study, and that did not change. The probability of success is the same. So here, each person in the study had a 50-50 chance of being over or under a situation of being on target. So again, that probability model is built assuming that the males are on target. Trials are independent of one another. In the context of this problem, what that means is that the intake of vitamin A from one person is not influenced by another person. So I believe that to be the case here. So what would a situation be where the trials would not be independent of one another? Let us suppose that maybe 5 of these males all lived in the same house together. So they were roommates with each other. And if one individual took their vitamin A intake one morning and then went around to the roommates and said, hey, you got to make sure and take your vitamin A today, or here's your vitamin A mineral, make sure and take that, then those might not be independent of one another. They might be influenced by some of the other males in the study. So aside from something like that occurring, I would assume that the intake of vitamins from one individual is not influenced by the other. So how to obtain the binomial probabilities in a spreadsheet? What I've listed out here is just, I think, 3 or 4 steps showing you how to get that done. What I did do down here a ways is just gave you a video that you could watch. So I provided a video for showing you how I did all of those steps in creating that binomial probability model. So instead of going through all of those steps, I'll just have you watch that video. It also includes information about, at the end of that video, of how to obtain the p-value for this problem. Okay, so again, the steps are listed out here if you'd like to go through and look at those. The binomial distribution function is what gets used here. I need the number of trials in there, I need the parameter value there, and I also need false specified at the end. Some of the common mistakes that students make when they're using this is they forget the equal sign, or they might forget the parentheses around the arguments that need to be passed into that function. And also you need commas between each of those arguments. There's 4 arguments that need to get passed into that binom dist function. This is what the binomial probabilities look like, all listed out with their associated chart that I created or graph that I created with those binomial probabilities. Again, creating that graph is shown in that video, and I have provided instructions here below as well. Couple of questions here for you to answer. So the one on the left here is the simulated reference distribution. The one on the right is from the binomial probability distribution. So just talk about the similarities between those two there. Question number 2 is just tell me what the interpretation of that probability value is. Here I happen to pick on an outcome of 5, which is about 12%, I guess. So I'll let you answer that question. Here's just all the math that is involved with computing that probability. So lots of steps there. Again, this is what the spreadsheet does for us. So we'll just let the spreadsheet do that. We're not going to worry too much about those calculations. When we're obtaining the p-value again, we need values as extreme or more extreme than the study outcome. So here that's going to be values 3, 2, 1, 0. And then on the right side it's going to be 11, 12, 13, 14. And those are the values that need to be highlighted when I'm in my spreadsheet. So you can see here on the screen that I need to highlight the values 3, 2, 1, 0. I need to highlight the probability values associated with outcomes 3, 2, 1, 0, which I've done here. If we add up these probabilities here, that would be the probability on the low side. I also need the corresponding values on the high side as well. So values 11, 12, 13, and 14, excuse me. Now for this particular reference distribution, this is a 50-50 scenario. And under a 50-50 scenario, those two probability values, the probability of low and the probability of high, are going to be the same. So I just need to add up the probability of low, which is 0.0287, and then I also need to add up the probability of high, which is also 0.0287. Again, these are the same because I have a 50-50 situation. The p-value here is 0.0574. Again, the nice thing about using a binomial probability model is that this is the exact p-value. If a different statistician decides to run this analysis, they're going to end up with exactly that same p-value. When those values are highlighted, I should have said when those values are highlighted like I have here, the sum of those are obtained down here in the lower right-hand corner. So down here in what's called the status bar, it actually has that sum of those cells that I have highlighted there. In order to highlight two different sets of cells that aren't next to one another inside of a spreadsheet, you need to hold down the control button on a PC, or I believe it's the command button on a Mac will also do the same thing. So I needed to highlight these cells, hold the control button down, and then highlight these cells here. And again, the computer will compute the sum of those down here in the lower right-hand corner for me. And that's my p-value, 0.0574. I'll let you go ahead and make the decision and write a conclusion again. Okay, that does it for part number 2, that does it for module 2, part number 5. Thank you.